Hello everyone. Now it's time to start the main part of topic 3b or topic 4 in new version, partial miscible systems or fully immiscible systems. Of course, we are talking about the non-ideal solutions, and you have learned about both negative and positive deviation. For positive deviation, if we have large deviation from ideality, it means that we have less affinity between like and unlike species and more repulsive forces. If this deviation strong enough, remember for positive deviation, if this effect is strong enough, then the liquid phase can split into two partial miscible systems. For example, water and butanol, N-butanol, normal butanol. Number of carbon is 4 for normal butanol. Here we have high deviation from ideality, and of course here we have positive deviation. Gamma is greater than 1 and less affinity between butanol and water and more repulsive forces. In this case, in some ratio, in some mixture component, we have two-phase region, two-phase liquid region, two immiscible liquids. Okay, an example is about different alcohols and water. If number of carbon, it means that organic side of alcohol is small. In this case, here we have fully miscible systems, for example, methanol and water. And if we increase the number of carbon atoms or increase the organic chain, here the miscibility decreases. Here we have deviation, larger deviation. And after propanol, 3 carbons, we get butanol. Here we have partial miscible systems. After butanol, for pentanol, where we have 5 number of atoms, carbon number of atoms, or organic side is 5. In this case, we have fully miscible systems. Okay, here you can see a description of our example, but in diagram, what happened to our diagram, what we can describe liquid equilibrium in diagram. In this slide, it's very important slide number 44, about the partial miscible liquids, where we have liquid two-phase region. So here you can see temperature versus composition again for component number 1. Again, here we have binary system, and we are talking about the component number 1. We can select component, one of the component. Okay, component 1, and you can see here we have this type behavior. In lower fraction, it means that lower concentration of component 1, where we have rich component 2, we have one phase liquid L2, which is contains this region L2 contains small amount of X1. Okay, we called it alpha phase, the first alpha phase, where the component number 2 is rich. Alpha phase or component 2 rich phase. So after special composition, here we have immiscible region. Here we have two-phase immiscible, two-phase liquids. Okay, here by increasing the amount of component 1, here we have another pure state or one-phase region, where we have high amount of component number 1. Here X2 is small amount and rich region of component 1. We called it L1, where we have large amount of component 1. Okay, here we have L1 region, liquid. Here we have L2 region, and here we have two-phase region, L1, L2. Okay, remember it's about the liquid region, not vapor liquid equilibrium, liquid equilibrium. Okay, here we have two phase, alpha related to component 2 rich phase and beta related to component 1 rich phase. Of course, x1 alpha can be found by any intercept for any temperature by this line, equilibrium line, and x1 in beta phase by this dotted line, x1 in beta phase. Okay, now for this diagram we have one point that after this point we have always one phase. After this temperature we have miscible systems. We call this temperature upper critical solution temperature. Upper critical solution temperature. Okay, after this temperature we have always one liquid phase. Below this temperature we have three regions, component 2 rich regions, component 1 rich regions, one phase, and two phase region, where here we have immiscible part. Okay, it's your task. Please try to find that how we can find the composition in alpha phase and beta phase. Of course, if you select the temperature, for example this gray line temperature below the critical solution temperature, upper critical solution temperature, in this case on this line, I mean from this point to this point. Okay, what happened to our compositions in both alpha phase and beta phase? Here remember, hint is degree of freedom. You should use Gibbs phase rule and find the degree of freedom. Of course, here one of independent variables is constant pressure. Then you can see that for this number of degree of freedom, temperature depends on composition, and vice versa. Composition depends on temperature and cannot independently change. So in this case, at constant temperature we have always constant composition on this line. So on this line, for any point on this line, we have always x1 for alpha phase and x1 for beta phase by these lines. Okay. Sometimes we have lower critical solution temperature. It depends on our composition. For example, 3-methylamine and water systems. After special temperature, we have one phase. By increasing temperature, we have immiscible region or two-phase liquid region. So we called it lower critical solution temperature. Lower critical solution temperature, L. Of course, at lower temperature we have one phase. At higher temperature, above the TL temperature, we can find two-phase region. For example, rich, this region is component number 2 rich region, one phase. Here we have component rich number 1, which it's ideal solution, of course, because x1 tends to 1 and x2 is a small amount. And here we have two-phase region, liquid 1 and liquid 2 in equilibrium. Okay, we called it lower critical solution temperature. And sometimes we have both a lower critical solution temperature and upper critical solution temperature. For example, some polymers and water, and we have nicotine and water, and other examples. In this case, we have both upper critical solution temperature and lower critical solution temperature. It's similar to island, and here we have one phase in left hand, in right hand again one phase liquid contain liquid 1, where compound 1 is rich, contain small amount of compound number 2, but here we have two-phase region. For all these systems, you can find the composition in each phase by this tie line and finding the x1 alpha and x1 beta, because here degree of freedom is 2 and we keep pressure constant. In this case, temperature depend on composition. Okay, and it's about the lower critical solution temperature. Okay, and island, upper and lower, both upper and lower critical temperatures. Okay, the next section is vapor liquid liquid equilibrium. It's very important. For example, we select this one. Okay, this one where we have upper critical solution temperature. If before this upper critical temperature, our mixture, it means that here we have two liquids, start boiling, what happened to this diagram?